Hello, everyone, and welcome to Signal Systems and Signal Processing with Wolfram U. The topic of this lesson is FIR filter design. In this lesson, we'll discuss FIR filter design using a method called the window method, which is a simple and effective method of creating linear phase filters suitable for most any signal processing applications. The method requires two steps. First, given a desired ideal filter specification in the frequency domain, we compute the impulse response by way of the inverse discrete-time Fourier transform. Then, we truncate and reshape the infinite impulse response that we obtained in the first step by means of an appropriate window sequence. Our goal here is to design a low-pass filter with a cutoff frequency of omega c. Let's first define a zero-phase ideal low-pass filter as shown here. If you look at the magnitude spectrum of the low-pass filter, we have a unit box over frequencies between minus omega c and omega c. The unit sample response will then be the inverse discrete-time Fourier transform of the frequency response. Evaluating the integral and simplifying, we have a sinc function for the impulse response. Here we show a short segment of the impulse response when omega c is set to pi over 3. The sinc function as unit sample response is infinite, and it is not causal, and therefore it is not practical. For this reason, we consider an approximation of the ideal frequency response by simply truncating the infinite unit sample response to make it finite duration. As an example, here we have an FIR filter of length 2n plus 1. Outside the window between minus n and n, the impulse response is 0. For n equal to 8, we have an FIR filter of length 17, as shown in this plot. The frequency response of the FIR filter will then be the Fourier transform of the sinc sequence with non-zero values from minus n to n. The magnitude response of the filter is not going to be as sharp as what we had with the ideal filter, obviously. And also, we have the ripples. It will not be smooth when we truncate the impulse response. Truncation, as we described, is effectively a multiplication by a finite length constant sequence of unit height, which we call a window sequence. It's called a rectangular or Dirichlet window. Plotting the magnitude response of the window sequence when n is equal to 8 shows the familiar sinc function shape. The Fourier transform of the truncated FIR filter, according to the modulation theorem for discrete-time Fourier transform, will be the convolution of the ideal frequency response that we are aiming for with the Fourier transform of the window sequence. Let's look at the frequency response of the low-pass filter again, this time for different values of the length of the window sequence, and also here we are plotting in the logarithmic scale. As we increase the length of the filter, note that the width of the transition region decreases, but the height of the stop band side lobe nearest to the cutoff frequency stays approximately constant at about minus 20 dB. It is independent of the length of the filter. This is a limitation, and for this reason, rectangular window is not suitable for many applications. Let's look at a shelving equalizer, which is a piecewise constant all-pass filter defined over two frequency intervals. These equalizers are used to amplify audio signals over a selected range of frequencies while leaving the remaining frequencies unchanged. For example, here we have a low shelf equalizer that amplifies the signal for low frequencies. Now, let's find a length 23 FIR filter that approximates this low shelf equalizer. With the given frequency response, the unit sample response of the prototype filter will be as shown here. Note that we have 2 pi here, and so for the value of the impulse response at n equal to 0, we can take the limit of the expression. Next, we truncate this unit sample response with a window from minus 11 to 11. And this will give us a filter with magnitude spectrum shown here. As you can see, it nicely approximates the low shelf equalizer. As we showed before, truncating the impulse response with the rectangular window has the stopband attenuation limit of 20 dB. For this reason, for applications where we need greater attenuation, we consider alternative window sequences. Here are the best known and most widely used windows listed with their definitions. Plotting their magnitude spectra, we can compare the attenuation and the width of the transition region. Note that the larger attenuation with these windows comes at the cost of wider transition bands. So for the FIR low-pass filter with cutoff frequency omega c equal to pi over 3, which we designed by means of a rectangular window, if needed, we can replace the rectangular window with a Hamming window of the same length as the FIR filter. That will make a new FIR filter with attenuation determined by a Hamming window. Checking the magnitude spectra of the original FIR filter and the new filter, as expected, the Hamming filter window substantially improves the stopband attenuation, but it also doubles the transition width of the filter. If this is a problem, we can reduce the transition width to be equal to the width that we had with the rectangular window of length 2n plus 1 by increasing the length of the Hamming window to 4n plus 1, almost doubling it basically. Here we show the magnitude spectrum of the filter smooth with a Hamming window of length 33. Now the stopband attenuation is improved without increasing the transition width. Given the audio clip of a piano key, here we see the magnitude spectrum of the audio signal. We want to filter the audio in such a way that all low frequencies up to and including the fundamental are retained and all the higher harmonics are substantially attenuated. Here is a close-up of the fundamental and its first harmonic. So to design our FIR filter, we need to have a cutoff frequency of 800 Hertz, roughly midway between the fundamental and the first harmonic. And let's say the width of the transition band should not exceed 500 Hertz. And we want attenuation in the range of the popular Hamming window, approximately 54 dB. As we showed before, the length of the filter is directly dependent on the width of the transition band and the desired attenuation. Here is a formula that is commonly used to get the length L of a low-pass or high-pass filter in terms of the value of delta F and A. Here Fs denotes the sampling frequency. So for our FIR filter, the length will be 53. Using the Wolfram language, we can get the filter coefficients of a low-pass FIR filter of length L with the normalized cutoff frequency that we want in radian per second, where the filter is smoothed by a Hamming window. This plots the magnitude spectrum of the FIR filter. Now let's apply the filter that we designed to the audio signal. For this, we need to take the convolution of the two signals. We could also use the Wolfram language to apply the filter. Comparing the magnitude spectra of the two audio clips, we can see that the filter achieves the criteria. We can also improve the window method of FIR filter design by using adjustable window sequences, where the shape of the window can be determined directly from the stopband attenuation and the width of the transition region that we want to have. The Kaiser window is a commonly used adjustable window sequence. The discrete-time Kaiser window is defined as shown here, where I0 is the 0th order modified Bessel function of the first kind, and alpha is an arbitrary non-negative real number that determines the shape of the window. It determines the trade-off between the main lobe width and the side lobe level, the attenuation. This is a central decision in FIR filter design using the window method. You can see how changing the shape parameter alpha affects the Kaiser window and its magnitude spectra. The parameter alpha controls the stopband attenuation of the FIR filter. The two window parameters, the length L and the shape alpha, are computed from filter specifications. Given a desired gain value delta, or given the desired attenuation in decibels A, the shape alpha and the filter length L can be computed using the two formulas shown here. A is the attenuation, and delta W is the normalized transition width in radian per second. Let's calculate the Kaiser window for a desired ripple of 80 dB and a transition width equal to zero point 0.2 pi. Defining the shape parameter, we can find its value at 80 dB, and also for the length using the formula, we get an odd length Kaiser window of length 53, which can be obtained using the Wolfram language as shown here. We can also show the Kaiser window and the magnitude of the discrete time Fourier transform of the Kaiser window. Now, if we apply the window to the unit sample response of an ideal low-pass filter with cutoff frequency omega c equal to pi over 3, the magnitude response of the resulting filter shown here meets the desired specification. In this lesson, we discussed the window method for designing FIR filters, which starts with an ideal frequency response prototype of the desired filter, followed by obtaining the impulse response of the ideal filter, and continues with the selection of an appropriate window, either fixed or adjustable, that would give us the desired filter specification. We saw that the FIR filter will then be obtained by a product of the two sequences.